So let's begin talking about electric fields and not only the representation in terms of lines, but also where they actually come from. So we're going to want to know the equations that surround um, the production of electric fields. I've drawn here just a crazy electric field that, I don't know what that function is. But it doesn't matter. The point is that there's an electric field here. According to what we learned in the last video, you know that if you place a positive charge somewhere in here, you can expect to know what direction that force is and what the magnitude of the force is, depending on what the field equation is. So typically we're going to have something a little simpler than that. We're going to have something that looks a lot more like what we had in the last video. Pretty frequently you'll see this kind of field. So for students, there tends to be a lot of confusion that surrounds this aspect of electric fields. What electric fields do to charges, and then also where they come from. We want to make sure that we're distinguishing that in your mind clearly. Here we have an electric field that we can count on to, if I give you a value, let's say, um, is equal to 2,000 newtons per coulomb. I want you to be prepared to determine what the force is on a particular charge. Remember that this equation is one that we can depend on. It's a definition, so it will always be there for you. Any electric field that is given to you will produce a force. But there are a lot of other ways that electric fields can be produced by charges, and I want to make sure that you're not confusing this charge, which is placed in an electric field, with the charges that are actually forming the fields. Here, we have not introduced any charges that are forming the fields. They exist, but we're just not showing them to you, and it doesn't matter. As long as you have this electric field, then you can place something in there and it works great. But it is handy to know more about these electric fields and what causes them. First of all, I wanted to introduce the idea that the field lines here you can see are very dense, and here they're not as dense. So this field representation is going to indicate that the electric field strength down here at the bottom would be about half that of what you would see at the top, because there are half as many lines in this volume. In other words, electric field is really a field density. If we were to go back and look at this example, then we would see that the density here is much larger than the density over here, and therefore the field strength here at the bottom is much stronger than the field strength here at the top. Let's address the idea that this field is created by charge. Every field line that you see here either comes out of a positive charge or goes into a negative charge, or both. So, in order for us to create a field, we need positive charges or negative charges. Let's explore how that begins. If I just take a positive charge here, I immediately create a field that emanates from that positive charge. All the positive charges that we've looked at so far this semester have all been creating fields. We just weren't talking about those fields. What is the equation that's represented here? Well, the electric field strength surrounding a single charge turns out to be a really simple equation. We can say that the electric field due to I'm going to put a little p here for a point particle. The electric field due to a point particle is equal to the Coulomb constant that we've already discussed times the charge that creates the field divided by the distance from that charge to a point of interest squared. Now, what does this R mean? It means that what I've done is taken a point over here, let's say right there, any point that I choose. I've just selected this one at random. You throw a dart, hit the dartboard, there it is. Then what that means is that I am now interested in the line that goes from the charge to the point. That line is R. It's important to keep in mind that the electric field is something that permeates space. P here is just a point in space that I've selected. There doesn't exist anything there. The electric field is only a mathematical idea that permeates this space. There's no charge here. There's nothing physical located there. I'm just selecting a point. And then R describes the distance that we talked about from here to here, to our chosen point. What this means is that the electric field is going to change its magnitude according to how far away things are. So if I chose a point here instead, then that would be here I would have R1, here I would have R2, here I would have 0.1, here I would have 0.2. These are going to have two different magnitudes. Now, if I were to choose another point, 0.3, over here, note that it has the same exact radius as 0.2, and therefore the electric field here at 0.2 would be equal to the electric field value at 0.3, although they're pointed in different directions. As for direction, you can, if an electric field is pointed to the right, you can label that as an X direction. If it's pointed upward, then you can label that as a Y direction. But if it's not pointed in either one of those, then you have a hard time putting that in terms of X and Y. So we simply say R hat. Now, don't worry too much about this. You're going to see this little R hat sitting on the end of things. All it is to tell you that is outward, right? That's all that means. So don't sweat too much about it. Now, the reason that we put this equation out there is because it is the equation from which all fields are derived. If I take 2 point particles, then I will have an electric field that's due to both point particles, and we'll discuss that in another video. If I have 100 point charges, then the electric field that shows up in the space that surrounds those 100 point particles will all be described by 100 of these equations. So hopefully we would really like to find a better way to talk about that using calculus rather than having to calculate up 100 of these equations. And we'll also address that in a separate video as well. So here our objective is to make sure that you're clear that this equation is true no matter what the electric field is. This equation takes charge that is present and determines what the electric field is. So essentially, if I put a charge here, say right here, well, I'll tell you what, let's move that over here to this point, P1. Then if I find the electric field here, let's say that my charge here is equal to 100 nanocoulombs, and I want to say that my distance R1 is equal to 55 centimeters, then I would have an electric field at point 1 that has a magnitude of 8.99 times 10 to the 9 Newton meters per coulomb squared, Newton meters squared per coulomb squared, times a charge of, we got 100 nanocoulombs, so 100 times 10 to the negative 9 coulombs, and divide that by our distance of 55 or 0.55 meters squared. That gives us 2,970 newtons per coulomb at that point. If I were to take another charge, now this one I'm going to go ahead and label as being little q, because I have my big Q here that creates the field, and I'm going to take a little q and place it in the field that is being created by the other charge. And so typically the big charge that creates the field will be big Q, and the little charge that we place in the field here will be little q. So remember, this charge creates this field, and this charge is placed in the field. When we do that, we can now determine what the force is on that charge. The force would be Q times E1, where this charge, let's put it at a value of -2 nanocoulombs. So that would be -2 nanocoulombs, or -2 times 10 to the negative 9 coulombs, times 2,970 newtons per coulomb, and that will give us 5.94 times 10 to the negative 6 newtons. And that is negative. The negative sign indicates that the force on this charge is inward rather than outward. Remember, because R stands for out, so if it's negative, then it's not out, it's in. It's positive, then it's out. Okay, so I could take that same charge and place it at some of these other points and get a separate force value. Now, it is also possible to have a point charge that does not create fields that go out, but instead that go in. A positive charge would produce outward lines. Negative charges produce lines inward. As I mentioned before, all electric field lines either have left a positive charge or are terminating at a negative charge, or both. It's totally possible for them to do both. So, in this instance, if we were to take our negative charge and place it here, we have now a big Q that is negative and a little q that is negative. And so we would have an electric field that points inward, and therefore the force would be opposite of that electric field and would point outward. It would still be the same magnitude. We would still have an equation that, an electric field of a point particle, that would be Coulomb's constant times this originating charge here, Q, times the distance between this charge and any point that we choose. I might choose this point over here just for the heck of it, squared, right? Pretty soon we're going to see an equation that looks a lot like this and doesn't have a square, so keep that in mind. Some of these equations you're really going to have to take a look at carefully and understand the difference between them and when they're used and when they're not used. If you have electric field lines that look like this equation does not belong anywhere over here. Now, yes, I did say that this is the originator of all electric fields, but the way in which it originates them is very complicated if you don't have one point charge. Here, there's definitely more than one point charge causing this field, and we will explain how that works at a later date. For right now, it's important to know that if I place a charge Q in this field, this equation has no place being over here. It doesn't determine what this electric field is. This electric field should be given to you already. It's constant. It means that if I put an electric field of value of 490 newtons per coulomb in the x-hat direction, then that means that you can count on it right here, right here, right here, right here, right here, everywhere is always going to be that value, right? Here, when I place a point charge into empty space, it creates a field, and that describes what that field is. So it's important to keep in mind that you've got two separate ideas here involving electric fields. One is that I give you an electric field and you determine what the force on a charge is in that electric field, and the other one is that I put a charge in empty space before there is any field, and we determine what field is created out of that point charge, or more than one point charge. Okay, so as we move on, we'll see how to incorporate multiple charges.